Welcome to a lesson on modeling data with trigonometric equations. In this video, we will be looking at how we can take a sine or cosine function, or how we can determine the sine or cosine function that models a given set of data. And we've already kind of done that when a few weeks ago when we were given a graph and we tried to write the sine or cosine function. So it's the same process, we're just looking at numbers, just at data instead of a graph. And then the second thing we'll look at is an application of harmonic motion. So let's just kind of quickly review what our sine, cosine functions look like and what the different components of those functions represent. So again, our format is y is equal a times the sine or cosine of the quantity b times the second quantity x minus h, and then all plus k. So if you remember what the sine graphs look like, the sine graph started at that middle line and it went up to the maximum, back through the midline down to the minimum, and then back up to the midline. So again, that was our normal sine graph, and if it was reflected, again, it would just be opposite, upside down. And then our cosine graph normally started at the maximum, went down through the midline to the minimum, and then back up to the maximum. So those are our two standard graphs. Remember the midline, so kind of the horizontal line that cuts right through the middle of the graph. It is the average of the max and min, so it's the max plus min over 2. The amplitude, which is half of the total distance, so that's max minus min over 2. We then talked about the period, which the period is the distance of one cycle. So how long does it take for one complete cycle to complete itself? And the easiest way to compute that was going from maximum, the distance, horizontal distance from maximum to maximum. Or you could also do the horizontal distance from minimum to minimum. Or you could take the horizontal distance from one max to the next minimum and then double that. And so that will give you the whole period. And then define the horizontal shift, which was the b in our equation. We take 2 pi and we divide it by that period. And then define the phase shift. That's going to be our x value. And so we're going to figure out, we're going to find that out by looking at the first x coordinate. And again, it's a little tricky. For the sine graph, we want to look at the first time the sine function is hitting the midline, and for the cosine function, we want to see when's the first time it's touching the maximum. And again, it could, if we reflected it, could be at the minimum. But again, that was sort of the general idea of how we use the graphs to write out the equations. So let's look at a data where or an example where we're actually modeling data. So what we mean by data is kind of what you see here. It's just a table of values, right? So we have an x column that ranges from 2 all the way up to 148, and then we have a corresponding function values or y coordinates. And if you notice, they start at 6, and then they slowly work up to 14, back down to 2, back up to 14, back down to 2, and then the table ends at 7. So we have this periodic data. What we mean again by periodic is this up and down fluctuation, and we're talking about the y coordinates, the function values. They're fluctuating up and down, so they're not staying they're not following a linearly increasing pattern, or they're not following some sort of quadratic increasing pattern or decreasing. They are sometimes increasing and decreasing and increasing and decreasing, and there's this repetitive pattern. So what we want to do is be able to write out what the equation of either the sine or the cosine function would look like that would model this data. And by modeling, we just mean we want to find the equation that would be the closest fit or the closest match to what the table of data looks like. So in order to do that, we'll start with we can do kind of both sine and cosine function. But we need to figure out our 4 constants. So we need to figure out the midline, the amplitude, our period, and our horizontal stretch, and then our phase shift. So to do that, I think there's a few things I think it's kind of helpful to just go through and highlight. So the first thing I want to look through is just in the function values in the y column, we want to find the highest values and then the lowest values. So where's all the maximums and the minimums? So we have a maximum at 14. That's the highest value. And again, it's a maximum just because the adjacent numbers are 12 and 12. So 14 is bigger than all the numbers around it. And then we get down here to a 2. That would be our lowest number because it goes back up to 9, and then we hit 14 again, which is a maximum, and then it goes 8, 5, 2, and we have a minimum again. And then it goes back up to 7, and it will keep hopefully repeating. So right off the bat, we can see our maximum and our minimum values. Okay, so from just those two values, we can compute our amplitude and our midline. So the midline, which we usually refer to as K here, it was the average of the max and the min. So if we take the maximum plus the minimum, divide it by 2, that's going to be 14 plus 2 over 2, which is 16 over 2, or 8. And then we know the amplitude would be the max minus the min over 2. So 14 minus 2 over 2. And 14 minus 2 is 12, so 12 over 2 would be 6. So just from the two maxes and the mins, we can figure out the midline and the amplitude. So those are the y coordinates, those deal with the vertical stretches and the vertical shifts. The next part we want to figure out is more horizontal type stuff. So what's the horizontal stretch, which is our period, and then what's our horizontal shift. So to find those, we kind of need to look at the y values, but we really want to pull out the numbers from the x coordinates. So if we remember, to find the period, we want to find the distance from one maximum to another maximum. So we know one maximum, the first maximum is 14, and it occurs when x is equal to 23. And then the next maximum occurs when x is 95. So we want to know how far is it from 23 to 95. And so to find our period, we're just going to subtract those. And you always subtract the larger number minus the smaller number, or if you had looking at a number line, it would be the right number minus the left number. So 95 minus 23. And that would be 72. So we know the period length is 72 just by comparing the distance between the two maxes. If you wanted just for fun, or if you wanted a different view, you could look at the minimums. So we have one minimum, the minimums are 2. We have a minimum at 59 and another minimum at 131. If you were to subtract those, you would also get 72. Okay. And again, you could also go from a maximum to a minimum, so from 23 to 59. And again, so that may not come out to be 72 right now because I'm not computing it at the moment, but we're not always going to see a nice uniform value. So maybe when we computed the distance between the maximums, we got 72, but when we did the distance, just for example, say from the minimums, we only got 70 or 71. So again, real data is not all nice and uniform. It's going to be sort of randomized a little bit, so there's going to be a lot of variation. And we may not even see both the maximums at 14. So maybe one was 14 and the other was 13 or something like that. So you don't have to find the exact same numbers, but they should be pretty close. And so again, modeling is just kind of a best guess, a best fit. So, there might be even a little variation in the answers that we come up with as we're working through these. So we have the period now. It's a period of 72. And once we know the period, we can find the value of b in our equation. And we did that by taking 2 pi and dividing it by the period. So 2 pi divided by 72, the 2 goes into 72 36 times. So we're going to be left with pi over 36. All right. And then the last thing that we need is our phase shift. Okay. And so one thing to point out, the midline, the amplitude, and our value for B, and the period, all four of those are going to be the same regardless of whether you're doing sine or cosine. So those three values in our equation don't change regardless of which equation you're going with. The starting values do. So to find our phase shift, we need to find, again, we're trying to find the x value at the midline, and this is for sine, and for cosine we want to find the x value, if possible, at the maximum. So that's going to be for cosine. So looking at our midline, let's do cosine first. So let's look at the maximum. Where's the first maximum we see? First maximum is 14, and that occurs at x equals 23. Okay, so for cosine, so if we're going to do our cosine equation, we know x has to be 23. So what about sine? The sine's a little harder, I think, here. Sine is when the function hits the midline. Well, we already found the midline, it's 8. So where do we see 8 in our data? So we're looking at y coordinates here. So the data goes 6, 10, 12, 14, 12, 8. So here's where we see this first 8. Okay. Notice that these values, as we cross this 8, we go 12, 8, and 2. And so it's actually decreasing, which is fine. We can use that. But ideally, we'd like to get the very first time it hits 8. And it's not visible in the table of data here, but there is an 8 that would have happened previous to the 8 that we just found. And it happens up here between the 6 and the 10. So again, the data, we can think of the data as representing a continuous curve. So if it goes from 6 to 8, there has to be a 7, 8, 9 between those. So somewhere in between 6 and 10, it has to hit an 8. Okay? And so we need to figure out roughly what's the x coordinate that's going to happen at. So if we look at the 6, 8, and the 10, 8's like right in the middle. So what would be right in the middle between 2 and 9? And to find that out, we could just do their average. So 2 plus 9 over 2 would be 11 over 2, or as a decimal, if we want, we could say that's 5.5. Okay, so again, it's a little weird because that 8 that we are looking for was not actually in the table, but it's technically there if you thought of this as a continuous curve. So the x coordinate we're going to use is that 5.5. All right. Okay, so we have all the information we need to write our equations then. So let's go ahead and do sine. So we have f of x is equal to the amplitude, which is 6, times the sine of the quantity pi over 36, because that's b, times the quantity x minus 5.5, that's our phase shift, that's the h value. And we close our parentheses, and then it's plus k, so in this case plus 8. And then if we wanted to write cosine, again, it's pretty much the exact same equation. We're going to have 6 times the cosine of pi over 36 times x minus, this time we're going to use the x coordinate for cosine, which we said was 23. We close our parentheses, and again, it's a plus 8. So those would be kind of the best equations that we could come up with, just with the process with the that we have at this point. Okay. All right, let's look at another example. So again, same thing, just different values. So we want to find the sine and cosine function. And our x column starts at 2 and works its way down to 60. And then our h values, or our y coordinates, start at 20. It goes up to 23, goes down to 17, back up to 23, down to 17, back up to 23, and it keeps doing that all the way down through the bottom of the table. So let's go ahead and figure out all of our values here. So to do that, let's go through the table and just kind of highlight where's the maximums and the minimums, and just any of those other values and distances that we're going to need. Okay, so our highest value, our maximum, is 23, and it happens several times in our table. And again, this is just made up data here. These numbers are nice and uniform. I mean, they're not completely spaced out perfectly. You know, they're not all 3 units apart or anything like that. But so 20, and every time it hits 23. So in real life, again, it's not always going to be nice and uniform. Like, you're not going to have consistently 23 all the way through this. You might see a 23 and then a 22 and then a 23 and a 24. So it would be kind of random. It would technically be probably decimals too, but so again, it won't be perfectly uniform. And then let's look for our minimums. So 20, 23, 21, 18, 17. So 17 would be our first one. 17 again, 17 one more time. So we have 17, we have 3 minimums that occur in our set of data. So from those we can find the midline and the amplitude. To find the period, we need to find the distance from one maximum to the next. So, and now we're talking x coordinates. So the first maximum occurs at x equals 6. The second maximum occurs at x equals 22. And so we want to find that distance there. And again, we could find the other distances. So from the second maximum at 22 to the third maximum at 38, we could do that maximum there as well. Hopefully, again, in real world, you probably want to look at all those periods and then kind of average them together. But this is just, again, just made up data for an example here. And then we need to know what, for sine, we need to know what's the value, the x value when it hits the median or midline, which we're going to have to come back to that. And then we need to know the x value for the maximum for cosine. So the very first maximum of 23 occurs when x is 6. So there's the x coordinate we're going to use for cosine. Okay, so let's go ahead and take the information we have so far and compute as much as we can. So for the midline, that's k, that's the max, the average of the max and the min. So we have 23 plus 17 over 2. And so 23 plus 17 would be 40 over 2, which is 20. And the amplitude is their difference, so 23 minus 17 over 2, and that would be 6 over 2, or 3. So think about this midline. That's knowing where 20 is the midline, that's important for our sine function, because that's where it's going to start. So we want to find where's the x value for when it hits 20 the first time. And the nice thing here is 20 is the very first value, and that's when x is 2. So there's our x coordinate for sine. So we kind of have almost everything we need here. We do need to compute a couple more things though. So we have our midline, we have our amplitude, we also need to get our period. And the period again is the distance from the maximum to maximum. So the first max is at 6, the second one is at x equals 22. So we're going to do 22 minus 6, which is going to be 16. And then we can compute the value of b by computing 2 pi over our period. So 2 pi over 16, which the 2 and the 16 reduce down to just pi over 8. So again, the the midline of 20, the amplitude of 3, and the b value of pi over 8. All three of those are going to be the same regardless of which sine or cosine function we pick. And then the only other two parts we need are the h values. So for sine, we know the h coordinate, again, is the first time it hits the midline, which we just said a minute ago was at h equals 2, or x equals 2. And then for cosine, we want to find the x coordinate where it hits a maximum. You could also do a minimum if you want, but that occurs at 6. So we have h is equal to 6. All right, so we have everything we need to write out our equations. So h of x is equal to our amplitude, which is 3, times the sine of b, which is pi over 8, times the quantity x minus our phase shift for sine, that is 2. Close our parentheses, and then plus 20. And then for cosine, it will be very similar. H of x will equal 3 times the cosine of pi over 8 times the quantity x minus, this time we're going to use the x coordinate at the maximum, which was a 6. Close our parentheses, and plus 20. All right, let's look at another, one more example here with data. And this one, I'll just warn you, it's still pretty nice, but it's not perfectly uniform like the last examples that we've been looking at. So we have data that represents a person's blood pressure measured in millimeters of mercury. And it's after t seconds since they started recording their blood pressure. So we're going to have values of time from 0 seconds all the way up through 1.3 seconds, going by tenths of seconds. And then their blood pressure at 0 seconds, it started at 130 millimeters of mercury, and it dropped all the way down to 69 millimeters of mercury at 0.4 seconds, back up to 129 at 0.8 seconds, down to 70 at 1.2 seconds, and then it starts to come back up again. So we'll do a few things differently this time. First, let's find a sine function to model this blood pressure. So we won't mess with cosine, we're just going to do sine in this case. All right, so let's first, again, just like we did before, go through the table and highlight the maximum, the minimum, and then see if we can kind of highlight where the period is going to occur. So the highest number, so we have this 130, and that seems to be a maximum right now, but we'll kind of double check that here in a minute. So we have 130, it decreases down to 69, and then it goes back up to 129. So and then it's going to go back down to 70, and then it kind of finishes out the table. So two things to notice: the maximums occur at 130 and 129 millimeters of mercury. Okay, they're not the same. Again, I kind of mentioned that in the previous examples. And similarly, the minimums are 69 and 70. They're not exactly the same, but they are close. Okay, so when you're modeling data, you could kind of choose to do this how you want. You could average the two numbers together, so the average of 130 and 129 to get sort of a middle maximum, and you could average the 69 and the 70. It's up to you. I'm not going to worry that much about it. You could also go with, I mean, you can kind of however you choose to go with this. Okay. Again, to some extent, there's no perfect answer for this. So I'm going to say my max. Let's go with the 130, and let's say the minimum is the 69. We'll just go with the first two. Okay, so we'll call this 130 is our max, and the 69 is our minimum. Okay, so that gives us the max and the min. We also need to know how far it is from maximum to maximum. So the first maximum of 139 occurs at 0 seconds. The second maximum occurs at 0.8 seconds. And so obviously the distance there is going to be 0.8. So let's go ahead and compute all the stuff that we know. So to find the k value, it's the average of the max and the min. So we're going to say 130 plus 69 over 2. 130 plus 69 would be 199 over 2. And that's going to be 99.5. And then the amplitude is the difference. So 130 minus 69 over 2. That would be 61 over 2, which would be 30.5. Okay, so that's the midline and the amplitude. And we already know that the period is 0.8. And that means that B is going to be 2 pi over 0.8. And you could simplify that in different ways. I'm just going to leave it like that for now. So we have K, we have A, we have B. All that's left is H. Okay, and again, H is the X value. And for sine, it's the X value where it hits the midline. And our midline is 99.5, or about 100. So looking at the table, where's the first time the blood pressure reaches 100? So it reaches 100 here at 99. Okay, and that's at 0.2 seconds. That's pretty darn close to 100. So I'm not going to do anything fancy. We're just going to say that H is that 0.2. And one thing we should observe in this particular problem is that when our blood pressure is 99 at 0.2 seconds, notice that the blood pressure is decreasing from 121 down towards 79 and even to 69. So because of that, when we write our amplitude in our function, it's going to be a negative amplitude. So I have A, B, H, and K. And so that's all the numbers I need to write out my sine equation. So to write out my sine equation, we have B as a function of t equals a negative 30.5 times the sine of 2 pi over 0.8 times the quantity x minus 0.2, close the parentheses, plus 99.5. Okay, so that would be our sine function that models the blood pressure data. So we have a couple of questions here on interpretation. So what does the period of the data represent? Well, we know the period was 0.8. And remember, period tells you how long it takes to complete one cycle. So that means this person's blood pressure, completes, blood pressure completes one cycle in 0.8 seconds. Okay, another way you might be able to interpret that is that their heart, this person's heart, beats every 0.8 seconds. Okay, so there's different ways you can interpret that. All right, so what's the amplitude and the vertical shift? So the vertical shift is also the median. So the vertical shift, the median, the midline would tell us the median or the middle value of blood pressure. So the average value, so the average blood pressure, so the average pressure is how much? So what is our vertical shift? What's our midline? It was 99.5. So 99.5 millimeters of mercury. So that's what the midline tells us. And it may rise or fall by the amplitudes, which is 30.5 millimeters of mercury. Again, there might be other ways you can phrase that, but that kind of gets the point across. All right, and the last question, we just want to know what is their blood pressure at 2 seconds. Okay, and so we can just take our function, which was the blood pressure as a function of time, and just put 2 seconds in for t. So B evaluated at t equals a negative 30.5 times the sine of 2 pi over 0.8 times the quantity 2 minus 0.2, closing our parentheses, plus a 99.5. And using a calculator, that comes out to be 69 millimeters of mercury. All right, let's shift away from modeling data to an application on simple harmonic motion. And there's several types of harmonic motion, but we're going to just focus on simple harmonic motion. And so the idea of simple harmonic motion is that we have some object that's moving over time. So we think of it as a displacement. So it's moving, oscillating, if you will. So it could be oscillating up and down. So you could think of like a buoy sitting out on a lake or on the ocean. You could think of maybe a pendulum swinging back and forth. Or a spring going up and down, something like that. So it's just an object is being displaced up and down, left and right kind of a thing. It doesn't have to be those specific directions, but an object is being displaced in a periodic pattern over time. And so we have two equations. Again, they're the same basic thing, but displacement, if we use the sine equation, displacement d equals a times the sine of omega t. And the omega, it's a Greek letter, but it just kind of looks like a W. Or if we use cosine, it would be d is equal to a times the cosine of omega t. So the omega, that can be kind of confusing. It's usually the way we talk about it in like a physics class or engineering maybe. But it really is just the same thing as the b that we talked about in the previous equation. So this isn't any new equation. It's just we still have the amplitude and we still have the b value. We just are talking about it as omega instead of b. But we can still talk about all the same stuff. The a value out front is still the amplitude. We're not going to worry about whether it's positive or negative when we call it the amplitude, so we're just going to think absolute value. The period, again, we looked at this before when we talked about the periodic functions. Period was 2 pi over b, just as b was 2 pi over the period. So in this case, the period is 2 pi over omega. And now one thing that is new that we really haven't talked about, but it's frequency. And so if you compare frequency with period, they are reciprocals of each other. Okay, so if period is 2 pi over omega, then the frequency is omega over 2 pi. And again, we can also use the relationship that the period is the reciprocal of a frequency. So period is equal to 1 over whatever your frequency is. Okay, or you can flip that around and use it the other way. Depending on which one you had, you could say the frequency is 1 over the period. So they're reciprocals of each other. So what do they mean? So since we're talking about an object being moved over time, period tells you how much time it takes for one cycle of motion. So, the up, down, and back up to where it started. Okay, so period tells you the amount of time it takes for that to happen. In the last example, we weren't talking about displacement, but in terms of blood pressure, it took 0.8 seconds for the blood pressure to complete one cycle. Okay, that's period. Frequency flips those units around. So instead of length of time per cycle, it's cycles per time, number of cycles per time. So if something, if you're running and your heart rate goes up, that means your period gets shorter, but it means your frequency gets higher. Okay, so they're opposite relationships. So the period would tell you maybe your heart beats every half second. It takes a half second for your heart to beat. That's the amount of time it takes. Well, your frequency would mean if it takes a half second to beat, that means it beats twice per second. So the period would be half seconds. The frequency would be twice per second. Okay, and so usually when we talk about frequency, if we're talking about per second, the unit for per second would be the hertz. All right, so let's just look at a couple simple examples here. We want to write our simple harmonic motion functions. And again, just kind of two examples here, and then we'll look at a more involved application. But so for the first one, we are given that an amplitude is 1.2 meters. The frequency is 0.5 hertz, which is abbreviated Hz. And we're going to assume that the displacement at time equals 0 is 0 meters. Okay, so in other words, it's starting at the middle of the graph. So we know from this statement, we know that this amplitude is 1.2. So we know A is 1.2. We know the frequency is 0.5, or if you wanted, you could write that as a half, a fraction. And so we're also going to need, I guess we don't need the period here, but we do need to find omega. And so we said a minute ago that the frequency was omega over 2 pi. So if we know omega, if we know the frequency is omega over 2 pi, and then we also know the frequency is a half, that means we could sort of set up an equation where we have 1/2 is equal to omega over 2 pi. And to solve that for omega, you just multiply both sides by 2 pi. And so that on the right side they cancel, and so we're left with omega would equal just pi, because you're taking 2 pi times a half, so that's going to give you pi. So we have, for our equation, the only two constants we need right now are the amplitude and omega. So those are the only two things we need. And the third part that we need to figure out is, are we doing sine or are we doing cosine? Okay, that's our third thing we got to figure out. And we can decide that based on the information we're given at the end of the problem. We're told at time equals 0. So when we start this whole process, there is 0 displacement. Okay, and so we're going to think of that as sine, because remember the sine graph starts at 0 displacement and goes up and down and so forth. Okay, so we're going to go with the sine equation. So to write our simple harmonic motion function, the displacement will equal 1.2 times the sine of pi t. Okay, and so that is our simple harmonic motion function. All right, let's try a second one here. We know the amplitude is 35 centimeters, so that's A. It's 35 centimeters. We know the period is 8 seconds. Okay, from the period we want to find omega. We know that the period has to equal 2 pi over omega. And if we solve that for omega, so we'd multiply the omega over, so 8 times omega is equal to 2 pi. We divide both sides by 8, so we get omega is 2 pi over 8, which would be pi over 4. So we have A, we have omega, we just need to figure out, is it sine or is it cosine? And again, in the problem, it tells us at the starting point, at t equals 0, the displacement is at its maximum. So the object is at its highest point. And that means we are looking at cosine. All right, so we have displacement is equal to 35 centimeters times the cosine of pi over 4t. Okay, and so that would be our displacement function. So they're very similar problems. In the first one, we gave you frequency. In the second one, you have period, but they're just reciprocals of each other, and it's not hard to figure out omega. And then in the first one, we're given a 0 displacement to start with, which is sine. In the second one, we have a maximum displacement, which is a cosine. All right, last example, just kind of put this in a bit more of a context here. So say we're tracking the high tides out at the beach, and we know that the average high tide occurred around noon on January 15th. And then we checked again, we found that the low tide occurred roughly 6.2 hours later. The average high tide occurred around noon on January 15th. Then we checked again and we found that the low tide occurred about 6.2 hours later, and then the next high tide occurred another 6.2 hours after that. We know that the water level is 2.5 feet above the mean sea level at high tide, and it is 2.5 feet below the mean sea level at low tide. So the three things we want to do is sketch a graph over a 24-hour period. We want to write an equation to model the harmonic motion, and then we want to figure out what was the level of the water at 10 a.m. on January 16th. So that goes a little bit, so just within the 24-hour period. Okay, so first let's sketch a graph. So we'll just kind of draw our x and y axes and stretch the x-axis off to the right. So we're going to assume noon at January 15 is t equals 0. And we know after at t equals 0, it was at its high tide. So this is the displacement is the y column, so we know, and then the x-axis is time. So at time 0, we know it has a maximum displacement. And we are told the low tide, which is the minimum, occurs 6.2 hours later. So after 6.2 hours, we're at the minimum. And then it tells us again we hit another maximum after another 6.2 hours. So after a second 6.2 hours, that would be at 12.4 hours. And so that would put us up here at a maximum. Looks like we need to extend our graph a little further. If we were to continue this pattern, we would have another minimum after another 6.2 hours, so that would be 18.6 hours, and then we'd hit another maximum after another 6.2 hours, and so that would be about 24.8 hours. And so our graph starts at the maximum, goes down to the minimum, back up to the maximum, down to the minimum, and then it ends about on a maximum. Okay, so that's sort of what our graph would sort of look like. Okay. So now we would then want to write an equation for our harmonic motion. And I guess one other thing we could add to the graph is we know what's the highest and the lowest point, because it tells us it goes 2.5 feet above and below. So the top part of the graph would be 2.5 feet, and the bottom would be a negative 2.5. So that's what our graph sort of looks like. That also tells me that the amplitude is 2.5 feet. And then we also need to figure out what is omega. So for omega, we need either the period or the frequency. And it looks like the period, so half period from high tide to low tide is 6.2 hours. And then from low tide back up to high tide is another 6.2. So it looks like the period is going to be about 12.4 hours. Okay. So to find omega, we remember that the period has to equal 2 pi over omega. So that means we have 12.4 is equal to 2 pi over omega. We multiply the omega over, so we have 12.4 omega is equal to 2 pi. And then we divide it over to get omega alone. So we have 2 pi over 12.4, which if you want, the 2's would reduce down, so you'd have pi over a 6.2. All right, so we have the amplitude, we have omega. We just need to know, are we going to use sine or cosine? Well, looking at the graph, it starts at high tide, right? So it starts at high tide, which means we are starting at the maximum, and that's cosine. So our displacement function, so this is part 2 here, our displacement function is going to be 2.5 times the cosine of pi over 6.2 times t. All right, so there's our equation that models the harmonic motion. So the last part is we want to figure out what was the water level at 10 a.m. on the 16th. So we got to just figure out some of the time here. So if we're going from noon, so from 12 p.m. on the 15th, and then if we went to midnight on the 16th, and then we're going to go from midnight to 10 a.m. on the 16th. So that's 12 hours from noon to midnight, and then another 10 hours from midnight to 10 a.m. So that's a total of 22 hours that we're passing from noon on the 15th until 10 a.m. on the 16th. So to figure out what the water level actually was, we want to know its displacement at 22 hours. So 2.5 times the cosine of pi over 6.2 times 22. And that's something we can compute on our calculator. Which if we do that, we will get 0.38. We'll just round it to 2 decimals. We'll get 0.38, and all of our units are in feet.